In standard physics, a definite location is historically treated as a free coordinate, a background parameter given to a system by default. The U-theory framework discards this assumption. It frames location as a paid state. This animated diagram visualizes the irreducible triadic quantum. To exist as a stable, measurable entity, a system requires three operational components: form, position, and action. Looking strictly at the position parameter, the P in our triad, we find it cannot function as a single variable. A definite location is bought with two non-substitutable subprices. The first subprice is space. A system must secure constrained spatial support, a relationally placeable distinguishability that prevents absolute coordinate overlap. The second subprice is mass. In the massive rest frame sector, mass dictates both the precise scale of localizability and the system's inertial response to a change in momentum. To exist anywhere in particular requires a dual payment, an exchange of spatial extent and an exchange of mass for relational placement within the universe. Redefining mass carries a professional risk. Without strict boundaries, it can sound like speculative philosophy attempting to overwrite quantum field theory or general relativity. The U-theory corpus prevents this through strict epistemic tiering. It separates the speculative, interpretive layers, designated L3 or L4, from rigorous formal mathematics, which are designated L1 and L2. Position mass duality functions as a precise rereading of standard mechanics through the FPA lens, leaving the underlying predictions of established physics intact. To transition from abstract philosophical interpretation into rigorous structural proof, we rely exclusively on the textbook limits of quantum mechanics. The model derives its mathematical power precisely by maintaining this epistemological honesty. The physical derivation begins exactly where textbook physics begins, at the scale where fixed particle number localization becomes sensitive to quantum field theory. This animated diagram shows the standard reduced Compton wavelength equation. By rearranging the terms, we expose a reciprocal identity. As mass increases, its corresponding localization scale becomes finer. Conversely, if mass approaches zero, the Compton wavelength approaches infinity, entirely removing the rest frame one-particle scale. At low velocities, this identical parameter sets the non-relativistic inertial corollary. Mass dictates the acceleration response of the system at a fixed force. The two anchors of this duality, the quantum localization limit and classical inertial resistance, are structurally governed by one identical physical quantity. This leads to an interpretive question. Why should a physicist read invariant mass as context? Under Mach's principle, inertia is not an intrinsic label. A mass's inertial response relies relationally on the distribution of all other matter in the universe. We observe a similar relational dependence in the Standard Model. Elementary fermion mass arises from coupling to the non-zero Higgs vacuum expectation value. It is an interaction-generated mass, not intrinsic physical friction. U-theory applies a specific interpretation to these interaction-dependent mass functions. Mass is crystallized context. Remove a system's context and its definite here dissolves. Concentrate that context and it manifests as the physical weight of localizability. This interpretation creates an immediate physical trap. If mass is the required subprice for a definite location, do massless quanta, like photons, possess a zero position score? This equation resolves the trap by modeling a nested, generalized localization meter. It accommodates both massive states and massless states through dual channels. When mass drops to zero, the massive rest frame channel vanishes. However, the overall localizability meter remains active through the detection channel. The formal math also provides a strong converse warning. A momentum eigenstate is delocalized across space, yet it retains mass. Mass enables a finite localization scale. But a delocalized state does not guarantee a massless state. Masslessness removes the rest frame here, but local detection events preserve the generalized position pillar. A photon is never scored as zero position. To cement this framework, we move into the rigorous Level 1 and Level 2 mathematical proofs, bounding localization capacity using quantum measurement theory. We define context formally as a positive operator-valued measure, a classical measurement channel regarding a position parameter x. This boundary demonstrates the mass-energy localization inequality via the Kramer-Rall bound. The bound proves invariant mass acts as a strict ceiling, upper bounding spatial Fisher information per unit of kinetic energy. While mass sets this ceiling, the measurement context determines the fraction physically realized. Mass defines the absolute capacity for localization. The measurement context realizes its accessibility. To earn empirical surplus, a theory must provide information that standard variables cannot. We evaluate this using a rigorous set of negative controls. Consider these variables. X standard represents everything standard physics already knows, like mass and momentum. Y is the outcome of a future experiment, and C is our proposed context variable. The framework establishes a no-go theorem. If context C is a deterministic function of known mass and coordinates, its conditional mutual information is zero. It adds nothing to predict Y. Empirical surplus requires a distinct, independently measured context observable, CR. For U theory to be falsifiable, this new observable must prove predictive power that mass and momentum alone do not. By proving its own empirical emptiness absent a new observable, the framework ensures it cannot rely on tautological philosophical loops. We have traced the sequence from the interpretive U-theory triad down to the rigid Fisher information limits of quantum estimation. The core thesis remains exact. Position pays twice. To exist locally requires an exchange of spatial extent, and for massive particles, crystallized context. The math maps the precise cementing of mass into a localized coordinate space. Position-mass duality formalizes the structural unification of inertia and localizability. To be anywhere in particular, a system must let the rest of the universe hold it in place. A here is context that has begun to weigh.